Hydrogen is the purest kind of energy. Pure hydrogen is only present in icebergs and glaciers, despite being the most common element in the universe. We use a number of methods to extract the hydrogen gas we want from hydrogenous materials. The water electrolysis process to create pure hydrogen is believed to be the most promising and environmentally friendly method. This environmentally benign method is restricted by the scarcity of freshwater, which is a finite resource in and of itself. Desalination could be a viable option, although doing so would significantly increase the cost and difficulty of making hydrogen. The challenges posed by creating green hydrogen are clear. So, should we give up on the idea of supporting electrolyte hydrogen and return to our old habits? Melbourne academic researchers, however, have opted for a different viewpoint. Testing has been conducted on a direct air electrolyzer, which draws hydrogen straight out of the air using ambient humidity. So how would they know how to pull off this incredible feat? We'll talk about it and the possibilities of this technology in the future. Prior to actually continuing, let's first talk about the production of hydrogen and electrolysis. A technique known as electrolysis divides water into two parts. Both oxygen and hydrogen gas are produced by using energy. This specific kind of electrochemical reaction occurs in an apparatus called an electrolyzer. Similar to fuel cells, electrolyzers feature an anode and a cathode that are separated by an electrolyte and operate in a number of ways. The main reasons for this are the kind of electrolyte the device employs and the many ionic chemical species it is handling. There are generally three types of commercial electrolyzers used to produce hydrogen. Given their durability, polymer electrolyte membrane electrolyzers are regarded as the most ecologically benign way to produce hydrogen. In this illustration, the electrolyte is a solid polymer. Water and the anode mix in an external circuit to create oxygen and positively charged hydrogen ions, or simply protons. These electrolyzers are often referred to as proton exchange membrane electrolyzers as a result. While the developed electrons from the electrolyte migrate preferentially toward the cathode and flow through the external circuit, the hydrogen ions react with the electrons from the external circuit at the cathode to form hydrogen gas. But why is this technique so special? The major advantage of a PM electrolyzer is its ability to operate at extremely high current densities. The process could run more cost-effectively because of its resistance to sudden voltage and power variations. The solid membrane also reduces gas crossing rates to guarantee safe storage. PM electrolyzers have an electrical efficiency of around 80% in terms of the quantity of hydrogen produced per unit of electricity used to carry out the reaction. This efficiency percentage is anticipated to range between 82 and 86% by the year 2030. Taking into account that new studies are being conducted every day. Now let's talk about a different kind of electrolyzer. Alkaline water electrolyzers are composed of two electrodes operating in a liquid sodium or potassium hydroxide alkaline electrolyte solution. At the cathode, electrons change water molecules into negatively charged hydroxide ions and hydrogen. These ions go toward the anode, where they experience oxidation, give off electrons, and transform into oxygen and water. Compared to PEM electrolyzers, these electrolyzers have substantially lower current densities and efficiency. However, these units are less expensive than their PM counterparts since they don't need expensive catalysts like platinum. They are also considered to be more resilient since they include liquid counterparts rather than solid ingredients, which are more susceptible to erosion. An innovative kind of electrolyzer that is relatively new to the market is the solid oxide electrolyzer cell or SOEC. These cells employ solid ceramic electrolytes to convert a water and carbon dioxide solution into hydrogen gas. PM and SOEC electrolyzers both use solid electrolytes. However, the kinds of electrolytes they use are quite different from one another. The primary components used in the production of ceramics are the clay, water, and earth minerals. On the other hand, polymers are man-made synthetic materials. The SOEC's typical working temperature range is between 600 and 1000 degrees Celsius. The high-temperature technique relies more on heat energy than it does on the electrical energy required for electrolysis to convert water into carbon dioxide. There are many more easily available electrolyzers than these three. However, even though they each have benefits and drawbacks, they all share certain characteristics. Cost is obviously a consideration. Before we can expect any large-scale production, we urgently need to reduce the cost from $1 to $2 since electrolysis is a very costly method of producing hydrogen. Freshwater availability, which is not always easy to get by globally, is another major issue. But it seems that we have a solution to that problem. Researchers at Melbourne University developed the direct air electrolyzer, which utilizes electrolysis to produce hydrogen gas by removing moisture from the air. So how does that system work? At any one time, there are 12.9 trillion tons of vaporized water in the atmosphere. The information may appear too good to be true, even in these dry areas where the relative humidity is often under 20%. Therefore, our water scarcity problem will be completely resolved if we can devise a method to convert that vapor into liquid water. Just that has been done by the research team. The DAE module comprises electrodes on either side coupled to gas collectors, and a water collecting device in the middle. The water collecting system also functions as an electrolyte store. By being saturated with liquid ionic chemicals, a porous material, such as melamine sponges, may absorb moisture from the environment. To deliver the collected water to the electrolytes, where the electrolysis takes place, diffusion is employed. Separate collections of hydrogen and oxygen are made from water, to verify the purity of the produced gases. In addition to keeping hydrogen and oxygen separate, the porous membrane also acts as a strong barrier, ensuring that the electrodes are completely isolated from the environment. The researchers experimented with different liquids, materials, thicknesses, and other properties, and found that their direct air electrolyzer can reduce ambient moisture to as low as 4% humidity. But hold on. The greatest is yet to come. The researchers were also able to get a 95% Faraday efficiency after some testing. Actually, more than PM electrolyzers. According to studies carried out by the researchers using electricity generated by solar panels, the DAE may be able to create 3.7 meters cubes of pure hydrogen per square meter of the cathode each day. The team also asserts that their system has little maintenance needs and is technically and structurally robust. Now let's talk about the possibility of this fantastic technology in the future. Scaling up testing under a range of challenging conditions and temperatures is one of the team's suggestions for the next stages. The DAE is now being scaled up from a 5-layer stack to a 1 meter square, then a 10 meter square, and so on, according to the primary researcher, Dr. Kevin Gang Lee. A dry climate may be simulated in the lab, but it is not the same as a real desert. We want to take it to Alice Springs for a few weeks to see how it performs. In short, Australian researchers have developed a novel kind of electrolyzer that can produce hydrogen gas from the atmosphere. After being connected to an energy source and exposed to air, it may produce hydrogen and oxygen gas by accumulating ambient moisture as low as 4% humidity. This ends the video for today. Hope you enjoyed seeing it. If you did, don't forget to like this post and leave a comment with your thoughts on the direct air electrolyzer. I'll see you again in the next video. Be careful till then.